everyone. First lesson of the new school year, we begin with Chapter 1, the number sets and interpreting graphs. We begin with the number sets because we'll be talking about number sets a lot throughout the school year, so it's a good place to start. So let's take a look at the real number set. So what is the real number set? The real numbers. The real numbers are made up of two subsets of numbers, the rational, we like to say the well-behaved numbers, and the irrational numbers. So let's take a look at the subsets of rational numbers. Okay, so we're going to start with the natural numbers, and here you see the symbol for natural numbers is the n. Okay, and I'll write this in raster notation, and I'll talk about raster notation a little more pretty soon. But what are the natural numbers? Well, the natural numbers, we like to say they are the counting numbers, the numbers you can count on your hand. Okay, it's the first set of numbers, man new. So in raster notation, I'll write that. Natural numbers in raster notation, we use this curly bracket, and that would be 1, 2, 3, and then the ellipsis to mean that it goes on forever. Okay, so that's the set of natural numbers, the counting numbers. And then back in the 1700s, okay, people realized that we needed the number 0, and so they included 0. And so the set of whole numbers starts at 0, and it goes on forever. So is every natural number a whole number? You bet, because the natural numbers, they're in the set of whole numbers. Okay, but is every whole number a natural number? No. Okay, because 0 is not a natural number. All right, and then sometime in the 1800s, okay, with the discovery of electricity, okay, people realized we needed negative numbers. So they included the negative numbers. Okay, like -2, -1, 0, 1, 2, ... goes on forever. Is every natural number an integer? You bet, because 1, 2, 3, 4 is in a set of integers. Is every whole number an integer? You bet. Okay, 0, 1, 2, 3 is in a set of integers. And then finally we have the rational numbers. And I'm not going to write that in raster notation. There's just way too many of those. But the rational numbers, when you think rational, think ratio. And when you think ratio, what comes to mind? If you said fraction, you're right. So the rational numbers include all the things you can write as a fraction: 0.5, which is 1/2, and 2 7/9. Well, you're probably thinking, well, -5 is not a rational number. It's included in a set of integers. But is it a rational number? You bet. You can write -5 as a fraction, -5/1. And ditto for 0, 0/1. You can write 1 as a fraction, 1/1. 2 as 2/1, I'm sorry, 2/1. But you get the point. All right, so those are the rational numbers. And then finally, we have the numbers you can't write as fraction, the irrational numbers, with the radical symbol, -5√3, pi, √2, √7/2, and number 8. Right? So, and they gave us, this computer, so they gave us, it has a mind of its own. So they gave us a symbol for rational numbers, Q, and the symbol for real numbers, but apparently they did not give us a set for irrational numbers. All right. So here, let's look at this here. Consider the numbers 0.6 repeating, 0.6 repeating. Well, how would you write 6 repeating? Okay, what is that? Is that a fraction, or is it not? It is a fraction. 0.6 repeating, you can write as 6/9. 6/9. All right, 2/3. Here, I'll show you something your middle school or junior high school teacher may have taught you. What would 0.1 repeating be? Well, I can tell you that would be 1/9. What about 0.2 repeating? That would be 2/9. What about 0.3 repeating? That would be 3 nights. How about 0.8 repeating? That would be 8 nights. How about 0.9 repeating? This is going to freak you out. Well, that would be 9 nights, or that would equal 1. Weird, but true. 0.9 repeating would be 1. I always like to do that with the middle school students. Strange, but true. Anyway, so 0.6 repeating is 6 ninths. That's a fraction. It's a real number. It's a rational number. So it's a real number. And it's also rational. Root 2, it's definitely a real number. Let's go back up to the table. Irrational numbers is in a set of real numbers. Okay. But it's just irrational. It certainly isn't a rational number. It's irrational. How about 0. Well, it's a real number, that's for sure. It's a rational number. You can write 0 over 1. It's an integer, okay, and it's a whole number. What about -5/2? Well, it's definitely a real number. It's a rational number, but it's not an integer. And then what about 0.5129? Okay, it's a decimal, but you can write that as a fraction. It's 5129 over 10,000. All right, so that would be real, and it would be rational. But it certainly isn't an integer, whole number, or natural number. All right, so hope this is making sense. So once you pause the video here, you can complete the table. Okay, see if you can classify each of those numbers, just as was done in the example for B. Pause the video and then come back. All right, the next thing we have to talk about is the finite set and infinite set of numbers. A finite set of numbers has a definite or finite number of elements. An infinite set has an unlimited or infinite number of elements. So how do you write finite sets? You write them using roster notation. So for example, the set of billiard balls is numbered 1 through 15. 1, 2, 3, 4, 5, 6, 7, 8, all the way through 15. Well, you're probably thinking, wait a minute, Mr. Winston. When you were talking about this set of natural numbers, oops, what happened to my image? Oh, there it is. When you were talking about the set of natural numbers, whole numbers, and integers, you used roster notation. Aren't those sets infinite? Yes, they are. Okay. Then the set of natural numbers, whole numbers, and integers, they go on forever. They are infinite. But in this case, I can write them using roster notation. And there's a specific reason why I can do that. Okay. You'll see why when we look at interval notation. All right, but I can use roster notation with that set. But I'm using the ellipses to indicate that they go on forever. What are those ellipses, right? That they go on forever. All right, so let's go back here. So there we have the set of billiard balls. And we use roster notation. If I said the set of the ages of students in the class, well, that probably would go like 15, 16, 17, 18. Again, I can use the roster notation. And then what about infinite set? An infinite set has an unlimited or infinite number of elements. How would we write that? Well, we write that in general using number lines, inequalities, and interval notation. Some of this may be reviewed to some of you. So let's take a look at all three. The set of real numbers between 3 and 5, meaning we're not including 3 and 5. They're between 3 and 5, which is also an infinite set. So you're probably, with the numbers between 3 and 5, how can that be an infinite set? Well, I'll show you. So certainly 3 and 1/10 is between 3 and 5. Or I can go 3 and 1/100. Or I can go between 3 and 1,000. Well, I can go on and on and on. I can go on forever. So there's an infinite number of numbers between 3 and 5. It is an infinite set. Now, we're not including 3 and 5, okay? We're saying between 3 and 5. So the way we would represent that on a number line, and it's not quite clear in this picture, we use an open circle to mean that we're not including the number at 3 and 5. Okay, think back to your middle school or junior high school days. And when we're working with inequality, remember the alligator always eats the bigger number. So I'm not much of an artist, but let's say here's my alligator. Whoa, it has a big mouth. Looks like a lizard more than anything else. Oh, where's the fig? Well, you know. Well, here's the mouth. The alligator always eats the bigger number. So I wish I was in class. How many of you guys remember that? Okay, so the alligator eats the bigger number. So there. So the bigger number 5 is on the right, and the smaller number 3 is on the left. But okay, so the alligator eats the bigger number. So the way we would represent that using an inequality is just as you see there. Okay. Now we weren't including 3 and 5. So when we don't include the numbers, we use open circles. And for inequalities, we use that. But what happened if we were including the numbers 3 and 5? Well, that would be a little different. Okay, there we would have the closed circles. We'll take a look at this a little more. Closed circles. But then we would include the number, the line underneath that. Okay, and to indicate that we're including that number. So this excludes, that excludes the number, and then this includes the number. All right, we'll come back to that in a second. Don't you just love my alligator though? Did you hear? Oh, make him green. Yum yum. So let's see here. An interval is a set of all numbers between two endpoints, such as 3 and 5. In interval notation, the symbol, the brackets are used to include the endpoints. And the symbols, the parentheses, are used to exclude endpoints. So let me just modify what I did up above. So if it's open, we would have parentheses. But if it's closed, we would have brackets. So there you go. So know that well. Right? So this is symbols when you exclude, symbols when you include. Let me make that a different color. Okay, yeah, let's let that stand out differently. There we go. All right, so excludes and includes. So in this case here, the case they gave us, we weren't including 3 and 5. We were not. And so we use the parenthesis. The smaller number goes on the left, and the largest number goes on the right, just like on the number line. But we're using parentheses between, but not including 3 and 5. All right, now let me ask you guys this here. So let's talk about infinity. Tell me the largest number in the universe. What's the largest negative number in the universe? You know it? I don't. Okay. So when we work with infinity, okay, because we don't know the largest number, how can you include something you don't know? Think about that. How can you include something you don't know? So with infinity, when we use the infinity symbols, we're always using open symbols. The parentheses. You don't know it. You don't know the largest number. You can't include something that you don't know. All right, so here, let's take a look at some of these examples. Numbers less than 3. So notice here, it's open at 3 because we're not including 3. But it goes on forever to negative infinity. So in interval notation, we have 3 open to negative infinity open. And then the inequality would be x is less than 3. X is less than 3. Let's look at the next example. So -2 all the way to positive infinity. It's closed at -2, so we use the bracket at -2, but it goes all the way to positive infinity, which is open. So there we would say x is greater than or equal to -2. X is greater than or equal to negative. There, easy way to remember this, and I always like to point this out. You see that inequality there? Well, believe it or not, it points the same way as that arrow. You see that inequality there? Well, believe it or not, it points the same way as that arrow. It points the same way. And then we have the numbers between 2 and 4. It's open at both ends. We're not including 2 and 4. Okay, but here again, this is where the alligator eats the bigger number. Okay, so 4 goes on the right and 2 goes on the left. But we don't have the equal sign because we're not including the numbers. And then finally, the numbers, including the numbers greater than or equal to 1 and less than or equal to 3. So it includes 1 and 3, all the numbers between 1 and 3. Including 1 and 3. So it's open at 3. I mean, it's closed at 3 and it's closed at 1. Okay, because we're including those numbers, right? And then again, so that would be x is less than or equal to 3 and greater than or equal to 1. And remember, when you have these two numbers here, like x is less than or greater than, remember the alligator always eats the bigger number. But the alligator mouth always points that way. Okay, it's his little mouth. All right. Oh, so I made it a point of, so when I was talking about natural numbers, whole numbers, and integers, now you start to see why I can't use interval notation for that set. Because in using interval notation for this set here, if I go back up here, I couldn't do this. I mean, I couldn't do this. Okay, I couldn't say, okay, 1 to infinity. Now, why is that not working here? Come on, there, 1, including 1 to infinity. I can do that with that set. Pause the video, tell me why. Okay, well, in order to, so this would imply, the reason I couldn't use that with a set of natural numbers, because that would imply I would have numbers like 1 and 2/5. Okay, or 7 and 2/9. Okay, I'd have every number that's greater than or equal to 1. I couldn't do that. But I can use roster notation, so that's why it's okay to use roster notation, even though it's an infinite set, the natural numbers, whole numbers, and integers. It's okay to use roster notation. But I'm using the ellipsis, those dots, to indicate it goes on forever. All right, so enough of that. So let's see here, the alligator. All right, so here we have some examples here. So use interval notation to represent each set of numbers. So the numbers that's less than 6 but greater than or equal to 4. So it's open at 6 and closed at 4. And here we have a compound set. So we have the numbers that's less than or equal to -2 and greater than or equal to -5. Okay. And so we have, so it includes -5 and includes -2. The numbers less than or equal to -2 and greater than or equal to -5. And then over here, we have the numbers that are greater than 3. So 3 to infinity. And then we join those two sets, those two interval notations with the OR. All right. So pause the video and see if you can write an interval notation for 2A and 2B. Pause the video and see here how you do. Okay, I've already talked about that. All right, here another example. Use interval notation to represent the numbers that are less than or equal to 12 but greater than 7. Okay, closed at 12 because we include 12. We have the equal. And we have it's open at 7, so we have the parentheses. All right. And then pause the video and see if you can represent an interval notation for 3 and 4. Numbers less than or equal to -8? That seems weird. And greater than -8? Guys, that's a typo on that problem there. Let's do this here. Less than or equal to -8 and greater than -8. Let's change that. That's kind of a goofy way to present that. So let's say here, -8. Oops. I'm using infinity. So x is greater than -8 and less than or equal to -2. So do that one. So write that using interval notation, and then write this one using interval notation as well. All right. Pause the video and see here how you do. Okay, the last thing we have to take a look at is interpreting graphs. So you'll have an assignment on Holt-McDougall. Okay, that will involve interpreting graphs, which I think to me is an essential, important skill for Algebra 2. Many of you are going to go on to calculus, and it's all about interpreting graphs. So let's look at this. A person decides to go for a run but must take breaks at certain points. The person's distance from the house is shown in a graph. So initially, before the person starts out, the distance they are from home is 0. Okay, and then sometime later, okay, they've traveled so many miles from home. Okay, they've traveled so many miles from home. All right, so line 1 represents someone walks to see their friend. And then line 2, well, they continue to walk but not as fast. And how do I know that? Well, if you take a look at the slope, okay, the slope for line 1 is a lot steeper than it is for line 2, which means that they were walking faster, okay, when they started out, but then they kind of slowed down. And 3, then they continue to walk but pick up the pace. All right, well, so now they're walking a little faster again. This slope is steeper than it is for 2. And probably walking faster than when they started, because the slope for 3 looks like it's greater than the slope for 1. But then when they get at their friend house, the distance, it goes nowhere because they're resting. Okay, they're there at their friend's house. Okay, so 4, then they take a rest at their friend's house. Okay, so maybe they traveled like 3 miles on line 1, 1 mile for line 2, and 2 miles for line 3. Okay, and then they're at their friend's house. Now they're going to go back home. So their distance is going to decrease. They're going back home. Notice here that the slope for line 5 is sloping down because they're going back home. The distance is decreasing. So then they walk back home at a quick pace for line 5, I'm sorry. 6, they continue to walk back home but at a slower pace. And how do I know that? Because the line for 6 is not as steep as the line for 5. But then they pick up the pace on line 7. They pick up the pace on line 7, and how do I know that? Because the line is steeper. The line for 7 is steeper than it is for 6. and then they kind of slow down right before they get home, because the line for 8 is not as steep as the line for 7. But then at the end of line 8, they're back at home. The distance is 0. All right, so the lesson, the activity on Hope McDougall will take you through interpreting graphs, which is a very important skill in Algebra 2. Maybe one of the most important. All right, so here, so your to do today, and this will be we'll be taking a look at the solutions, the answers on Friday. So when you do your homework, I want you to label your paper this way. Indicate the due date, so the due date is going to be 9/11. The problems you're going to do out of the textbook, and you can look on in the resources. If you don't have the textbook, you'll look at page 10, 5 through 7, 9, 15, 18, 20, and then 30 through 33. So those would be the textbook problems. But then on the Hope McDougall website, you'll go to the Interactive Student Edition, and you'll go into Unit 2, Module 3, and you'll go through Concepts 1 and 3, and then evaluate 1 through 14, and you'll see what I mean when you get there. Okay, now there's no turn-in for the Interactive Student Edition. The turn-in is when you go to take your test on Monday. You'll have problems exactly like what you see in the Interactive Student Edition. So go through it, okay? I'm not going to check to see if you go through it. I'm not going to look at your homework, although I do get indication, okay, that you've actually done something in Hope McDougall, but I can see if you've actually gone in there and I've done something, but I'm not going to collect it from you. I will collect it when you take your test, okay? All right, so make sure you go through that, and if you have questions on anything you see in the Interactive Student Edition, just let me know. Okay, so that's a wrap, guys. That's the first lesson.